Routing data through a global network forces a path through millions of intersecting nodes. At this scale, manual pathfinding is physically impossible. Dijkstra's algorithm solves the shortest path problem by mapping localized distances from a single starting point. Writing the code is only half the engineering challenge. We have to look past the mechanics and verify the underlying mathematical logic. First, why does a localized, greedy decision, choosing only what looks best right now, guarantee the absolute optimal path for the entire network? Second, how much computational time and memory does the algorithm consume as the size of that network increases? This is the balance of algorithm design. A mathematical proof ensures the logic works, while the data structures ensure that logic can scale. An algorithm is useless if it cannot guarantee both mathematical accuracy and operational efficiency under massive data loads. This routing scenario starts from a single source, node A, with two initial options to nodes B and C. We scan our immediate neighbors and identify the known direct distances from the source. The algorithm selects the node with the smallest unvisited distance and marks it permanently. Here is the critical theoretical challenge. Could an undiscovered, longer route eventually circle back to make this chosen node's distance even shorter? To prove why that is impossible, we rely on the core axiom of the algorithm, the monotonic guarantee. In a system where all roads have positive lengths, every additional edge added to a path increases the total distance. If we take an alternative route, we are adding a positive number to an already larger distance. The total cost strictly increases. An existing shortest path can never become shorter through subsequent discoveries. Under these conditions, marking a vertex as permanent is mathematically safe. Because accumulated positive weights only move upward, Dijkstra's localized greedy choice creates a sequence of verified optimal distances. This graph introduces a variable that disrupts the established rules, a route that subtracts distance through a negative edge weight. We trace the initial direct path from the source to the closest node, just like before. The algorithm applies its greedy rule, permanently finalizing this initial node based on the local data. Now we trace the secondary, alternative path that utilizes the negative edge. Combining a positive path with a negative edge creates a net retroactive reduction in total distance. A shorter path was just discovered to a node that the algorithm had already permanently locked. If a graph contains a cycle of negative weights, greedy algorithms can get trapped in infinite loops, continuously circling to decrease the cost. Unlike our earlier proof, the localized decisions are now blind to better long-term outcomes. If a network contains negative weights, Dijkstra cannot be used. It requires an alternative algorithmic framework. This loss of accuracy is a structural property of greedy algorithms. When negative values are present, the immediate minimum no longer reflects the long-term shortest path. The localized assumption that gives Dijkstra its speed is exactly what causes it to mathematically collapse when negative weights break the monotonic guarantee. With theoretical correctness established for positive networks, we have to address physical execution constraints, time and space complexity. This V by V grid demonstrates the first implementation, an adjacency matrix. Rows represent source vertices, and columns represent destinations. To find the smallest unvisited distance, the algorithm must linearly scan an entire row. If there are V total vertices, checking those connections takes order V time. That scan must be repeated for every single vertex in the entire network. V iterations multiplied by order V time per scan establishes our final time complexity, order V squared. For space complexity, this V by V grid demands an order V squared memory footprint, even if most of the cells are empty. This matrix structure is effective for a dense graph, where almost all nodes interconnect and those memory cells are actually utilized. But an order V squared complexity becomes computationally prohibitive when applied to vast networks with millions of sparsely connected cities. To scale the algorithm, we replace the matrix with an adjacency list and a priority queue, specifically a min heap. The min heap automatically floats the smallest distance to the top of the tree. Extracting the minimum distance no longer requires linear scanning. The algorithm simply plucks the top node. Removing that minimum and updating the remaining distances in a heap carries a time cost of order log v. Factoring in the total number of edges and vertices, this structure reveals our optimized time complexity, order v plus e log v. Space complexity drops to order v plus e. Since we use an adjacency list, empty connections are no longer stored in memory. This makes it ideal for a sparse graph, where nodes have very few actual connections relative to the total size of the network. In real-world routing, the logarithmic advantage of the min heap provides a significant performance gain over the quadratic baseline. The implementation difficulty increases, trading simple grid code for more complex tree management to achieve faster execution. Using a min heap allows Dijkstra to route massive real-world data in real time, making it viable for production-level global networks. This optimized, mathematically proven algorithm is the engine running the systems of the modern world. It drives consumer-level spatial routing and dynamic traffic navigation on your dashboard. It calculates minimum transmission delays and dictates path planning in automated machinery. But this reliability only exists within networks devoid of negative parameters. Engineering requires aligning the mathematical proof of correctness with the data structure optimized for the environment. When localized, greedy decisions cannot solve a problem, we must move beyond linear optimization and towards systemic exploration. This transition leads directly to backtracking.